Hello physics students, this is Dr. Brenzi here. This is lesson 5.1.3. And our objective for this lesson is that we're going to be able to calculate the minimum velocity an object needs to perform a loop-the-loop. So a loop-the-loop is, for example, a bicycle, or you could have a roller coaster that actually goes in a vertical loop. And we're going to find out that there is a minimum velocity that this bicycle or your roller coaster needs to go in order to perform a loop-the-loop. So what happens in a horizontal circle, first of all? So let's kind of review what we learned in our last lesson. So if a car is going around in a horizontal circle and there's no banking on the curve, in other words, it's not like NASCAR where you're going around and the road tilts. So just a flat parking lot type surface or a regular road. We have the force due to friction acting as our centripetal force, which is going to pull our car toward the center. And the friction force matches the centripetal force that is needed to put this car in a uniform circular motion. So the friction force will actually adjust itself so that it equals m times v squared over r. So if the velocity doubles, if this car decides, oh, I want to go twice the velocity, then it will need the 4 times actually the friction force, because friction force, or excuse me, centripetal force depends on velocity squared. So the centripetal force will have to be multiplied by a factor of 4, or it'll have to be quadrupled, or the car is going to end up slipping. And sometimes you've actually seen that, especially if you have seen car races. Wasn't expecting that to happen. That was a lot of information right there. So let's go through that slowly. So what happens in a vertical circle here? So I was thinking about a couple cases that I need to cover here, and let's say case 1, let's say that our car is able to apply enough force by stepping on the accelerator to keep this velocity constant all the way around the loop. So what would that look like? Well, if that's the case, then we know that the forces acting on the car at the very bottom are the normal force and the gravitational force. Well, the moment that this car enters the loop-the-loop, something interesting happens. So at the bottom, the net force has to equal m times a. Well, the acceleration is the car's centripetal acceleration. So normal force minus gravitational force, that's F net, equals m times centripetal acceleration. We can add gravitational force to both sides of that equation, and we can say, well, the normal force has to equal the gravitational force plus m times centripetal acceleration. Well, what does that mean? What that means is that the normal force is going to adjust itself so that it will equal this plus centripetal acceleration. So if this is a vector that represents m times centripetal acceleration, then we actually need a normal force so that if you take this plus Fg, so let me draw an Fg there in the positive direction, so my normal force has to be the sum of these two vectors, which means my normal force actually has to be greater than my gravitational force. Up until now we've been used to just motion horizontally, but once this car enters this loop-to-loop, it actually needs a larger normal force than it has a gravitational force. So be very careful about that when we start solving problems involving loop-to-loops. What ends up happening at the top here? Well, at the top we have our gravitational force still moving or pointing in the downward direction. So we can write F net equals m times AC. But now our normal force is also pointing in the downward direction. Because normal force is perpendicular to the surface, so both normal and gravitational force are pointing downward. My mass times acceleration, centripetal acceleration, is also pointing downward, so I need a negative sign in front of that. Now I'm not going to solve this one for net force because it's actually easier to visualize when I'm going to draw by looking at this equation. So we have a negative Fg right here, and if I have negative Fn, those two have to equal negative m times AC. Now because the velocity is the same at the bottom and the top, that means that this centripetal acceleration is going to be the same. So the normal force is going to adjust itself so that it equals, so that this plus that equals mass times centripetal acceleration. So at the top we have a very small normal force, and at the bottom we had to actually have a very large normal force. So the point I want you to get here is that the normal force is going to adjust itself so that the sum of these two forces is always going to equal mass times centripetal acceleration. And if you don't remember what centripetal acceleration is, you can look in your notes. Oops, not VC, AC. AC equals V squared over R. Okay. So you can see that how the normal force adjusts itself really depends on the velocity of this car in the loop. So large force, normal force at the bottom, small normal force at the top, and it will adjust itself so that this mass times centripetal acceleration will remain constant. I forgot I wrote something there before I wrote my centripetal acceleration formula. So let me back up here a little bit and erase this part. So the big thing to remember is that normal force is going to change. It's going to adjust itself so that m times centripetal acceleration remains constant. Alright. So let's think of another case now. Let's think of what would happen if the car just coasts in the loop. So at the bottom, you could probably predict that it's going to have a larger velocity at the bottom than it will at the top. So I've adjusted the vectors in my picture a little bit here so that the bottom velocity vector is larger than the top one. Now, because we're not applying any external forces to the car, the total energy of the car is conserved. So going back to Unit 3, we set the gravitational potential plus kinetic energy at the bottom equal to gravitational plus kinetic energy at the top. And what that's going to give us is that's going to give us a relationship between the velocity at the bottom and the velocity at the top. So the gravitational potential energy at the bottom is 0 because we have no height. So we have 0 plus 1/2 mv bottom squared. That's the total energy at the bottom. And then at the top we have m times g. And then what is the height of the car when it's at the top of the loop-to-loop? Well, that happens to be 2 times the radius of the loop. So instead of h, I'm going to put in 2 times r. And then, be careful here, when we're dealing with problems, when we used to deal with problems where we were throwing a ball up, at the top of the loop we would always say, oh, well, the vertical velocity equals 0. But at the top of the loop, the car still has a velocity, so it still has a kinetic energy. So be mindful of that when you're solving problems like this. Now, if you are in my advanced class, this is about as much as you basically need to know here. Because at this point, you're probably going to be given some numbers here, and you're going to have to solve for the velocity at the top, and you'll probably be given the velocity at the bottom. Or you might be given the velocity at the top and have to solve for velocity at the bottom. But those of you in AP, we're actually going to come up with an expression for the relationship between the velocity at the bottom and the velocity at the top. And we're going to do that algebraically. So, all I've done here is just rewritten this equation here without the 0 out in front. And then rearranged this expression so that the coefficient's out in front. And then I'm going to divide both sides of this equation by 1/2 m. When I do that, I get v sub b squared, on the left-hand side. And on the right-hand side, it turns out that I end up with 4gr plus vt squared. And then if we take the square root of both sides, I decided to solve for vt squared, and then take the square root of that, and it turns out the velocity on the top is equal to the square root of the velocity in the bottom squared minus 4gr. So there's a definite relationship between the velocity on the top and the velocity when you entered the loop-de-loop. And of course all of that's assuming that the loop-de-loop is frictionless. If you had friction there, then you would have to account for that somehow. And that would be a more complex problem. So, why doesn't the car fall at the top? After all, it looks like we just have gravitational force working here. And of course, if this car were sitting still, yeah, of course it would just fall straight down to the ground. But we have a car that is moving at a velocity v sub t. We have a gravitational force, and we have a normal force, because if we didn't have a normal force, this car would continue to go in linear motion that way, according to Newton's first law. So we have to have a normal force to bring this car back into circular motion and complete the loop-de-loop. So we noticed in a couple of slides ago that the gravitational force plus the normal force has to equal mass times centripetal acceleration. And remember, centripetal acceleration is going to be equal to v squared over r. So when it's at its top velocity here, or velocity at the top, the centripetal acceleration is going to be vt squared over r. So the normal force is going to change itself to keep the car in uniform circular motion at this given instant. So at this very instant, the normal force is going to adjust itself so that the car goes in uniform circular motion. So if I had a larger VT, what would happen? Well, that would mean, because of this formula here, I would have a much larger centripetal acceleration. As a matter of fact, it's so large I don't have enough room to draw it to scale. So I'm just going to draw a larger vector here. My gravitational force is the same, but I have a larger normal force. So the normal force has to adjust itself because I have a larger mass times centripetal acceleration. So a larger velocity at the top means we're going to have a larger normal force. Could the car possibly fall? Well, if the car goes slow enough, remember that gravitational force is always pointing down, but normal force if I have a small velocity at the top, that means I have a small m mass times centripetal acceleration here. And if this vector is not big enough to match this vector, I don't have a normal force that can possibly point up. After all, the surface is actually above the car. So if this velocity is small enough so that this vector is smaller than this one, I have no way of adjusting the normal force to keep this car on the track. So the normal force can't be positive at this point. It always has to be pointing down. So right now, in this particular situation, there's too much downward force to keep the car on the track. And we can actually figure out what velocity that will happen at. In other words, what velocity at the top will cause the car to actually fall off the track. So we need this vector mv squared over r to be at least as big as gravitational force. And if it's not, then we know the car is going to fall off the track. So the car is going to fall off the track if this is true. If this vector is smaller than that one, then that's all this statement says. And then if we solve for v sub t by, first of all, dividing both sides by m, that'll cancel the m's. And then we just end up with v sub t squared is less than g times r, or the velocity at the top is less than the square root of g times r. So if my velocity is small enough so that this is true, then there's going to be too much gravitational force to keep the car on the track, and our car is going to go whoop, whoop, and it's going to fall. Okay, so now you know the minimum velocity that is required for a car to complete a loop-the-loop. When we go into class tomorrow, we're going to actually learn how to apply this to particular situations. And hopefully we'll have fun with lots of loop-the-loops tomorrow. Okay, class, I will look forward to seeing you tomorrow. Bye.